Alright guys, this video is actually going to be short. That's right, this video is actually going to be short. Our newest chapter is going to be an extension of one of the previous chapters. That having been said, you need to go back and review how to draw Lewis dot structures on your own. You guys should be getting great at drawing Lewis dot structures by now. And you need to be able to look at a Lewis dot structure and figure out the molecular geometry of that structure. So here they are. Here are the 15 we've already learned. The standard ones: linear, trigonal planar, bent, tetrahedral, trigonal pyramid, bent again, trigonal bipyramidal, seesaw, T-shaped, linear, octahedral, square, pyramidal, square planar, T-shaped, and linear. And you guys are getting really good at these. And I don't know if you remember, but let's say T-shaped. T-shaped might have two names. You might say it's T-shaped, or you might say its its electron domain geometry was trigonal bipyramidal, because T-shaped has electrons going in 5 directions, 3 that are bonded and 2 that are non-bonded, 2 that are extra pairs. So that's a total of 5 directions, which is the whole family. Sometimes I call them families, but their electron domain geometry is in the trigonal bipyramidal family. So you need to be able to take these again and figure out the shape, because we're going to take this a step further. And while you're reviewing, go ahead and start smashing the angles into there. Now with the angles, there's 2 methods. One is just straight up hardcore brute force memorization. You know, some people make like little charts. I can't stand this, but they do it. But they say, okay, 5 directions, 0 extra pairs, and then 90 and 120, and they do that on a little flashcard. So on one side of the flashcard it says that there are 5 directions and 0 extra pairs on the central atom, and on the other side it says trigonal bipyramidal, 90-degree angles, 20-degree angles. And if you want to do brute memorization, you can. I don't really like it. There's the bell. I prefer, and this is me, I prefer imagining what it looks like. If I see a T-shape, I imagine what a T-shape looks like, and the second I see what the T-shape looks like in my head, I know the angle is about 90. Or if I see a linear, I know that the angle is 180. Notice that there is a slight change in the angle as we go from all bonds to an extra pair to 2 extra pair. The 109 becomes a little bit less than 109, becomes a little less than 109. What was 120, 120, 120 here? Bond pair squishes the 120 down. It's just a little less. We're not going to get specific as to how much less. I would not say, well, trigonal planar is 120. That's a pair of electrons. So no, that's 118. That says 180. What a moron. No, we're not going to do that, because the central atom has a big role in how that angle changes, and it depends on what the central atom is. But I think we can agree that if trigonal planar would be 120, the extra pair of electrons here, it looks like a weird alien, doesn't it? The extra pair of electrons is going to repel these bonds in just a smidge, so instead of 120, it ends up being less than 120. Like maybe 119 or 118 or 117. But it's not going to be 90 degrees. It's going to be a little bit less than 120. So let's take 30 seconds and let's practice for a second. So we're going to practice with these 4 molecules. The first one's going to be Selenium Tetrafluoride. So selenium has 6 valence electrons. Let's see, 6. 4 fluorines, each one has 7, bond, each one has 7, bond, 7, bond, 7, and bond. Now selenium's one of the ones that can exceed the octet, so we're good here. This is 4 directions and an extra pair. 4 directions and an extra pair is seesaw. So you've identified it as seesaw. Good job. You need to practice. Let's try the next two.
Okay, so the next one is silicon tetrafluoride. Silicon has 4 electrons in its valence shell. Chlorine has 7.
I don't know what happened there. Excuse me. So once you bond the silicon to the chlorines, you have 4 bonds. Obviously, that is tetrahedral. Good job. All right, so I also am going to do sulfur difluoride and xenon tetrafluoride. Sulfur has 6. This one's pretty simple. When I do sulfur and oxygen, I usually... Oh, that's not a very good electron. What is that? I usually go ahead and think about the fact that it's usually a bent shape. So I usually do 1, 2, 1, 2, 1, 1. So it's easier to see the bent shape. Now, if we're talking electron region, I wouldn't want to say bent. The number of electron regions is 4 on the sulfur. So this is also a tetrahedral as far as the electron region domain. Electron domain geometry. I always say that backwards. And that's what we want to focus on in this chapter. It's really the number of electron domains. Lastly, xenon tetrafluoride. And the reason I picked this one is both of these have 4. And so people go, oh, that's 4. That's probably tetrahedral. And they say, oh, that's 4. That's probably tetrahedral. But go ahead and take the minute it takes to draw it out, and you're going to see real quickly, and I'm doing a sloppy version here, is that there's 4 fluorines. Uh-oh, there's an extra pair and an extra pair. This is actually 6 electron domains. So that makes this octahedral. Octahedral. So, make sure you review your different shapes and be ready to rock and roll next class. The review video will be on the shapes. Also, we're only going to spend 3 days, 1, 2, 3 days on this chapter. We're going to do the notes next class. We're going to go over homework the second class, and then we're jumping right into a test. The test is going to be a small test. It's not going to be full points. Here, let's look at the rest of the notes. See, we're going to talk about the molecular orbital model, which involves orbitals. Whoa. We're going to talk about hybridization, which is how the orbitals blend together, and how to figure out the hybridization based off of the different geometries, which is why we're talking about geometries. We're going to look at what the heck is this drawing, pi and sigma bonding. We're going to talk about how double bonds and single bonds form. We're going to look at some organic chemistry and talk about how to read line structures for organic compounds. They are going to be talking about smiley faces. Evidently this one has a booger. Again, organic chemistry, figuring out the missing pieces. And the molecular orbital model theory is a lot easier than this looks because we're not going to get too deep into it. All right. Enjoy and see you on